Can we also talk about D?
Yes. So first of all, for 8b, if you lost points with t equals 2.750, show me after class, and I'll give you points back. Okay. And really, you might have lost points on B or C, so you have to check. For 8b, the equation is, and really this is t star. The equation is t star times the standard error, and this is for a single mean, so it's 5.99 squared divided by, 5.99 divided by the square root of 36, which is 6. This is the formula. Yes?
How much, excuse me,
Well, I did want to do D, but you can ask a question first.
sorry, it's not really about that. How many points were each part worth for that one?
So I split it up kind of weird. Part A was worth 3, part B was worth 3, part C was worth 5, and part D was worth 3. Yeah. So for part D, I would just say yes. Russell Westbrook's numbers, he had what, 36 triple doubles this season? No, 34. 36 was the number of players. That is way above the end of the confidence interval. The end of the confidence interval is 6. So we could say with 99% certainty that the average was less than 6, and he got 34, way above average. So I would say yes. And I didn't care too much about the explanations in that problem. Yeah?
Okay, 8B.
8b, yes. Did you lose points on 8b?
I got 2.
You don't have to answer that, I guess.
I mean, there's just 2 there.
8b was worth 3, so you lost a point.
So,
If
okay.
it's because you wrote t star equals 2.750 instead of what I used, then you can come see me after class to get a point back.
No,
And if it's for some other reason, you can still see me after class to ask about it,
Yeah.
and I'll just take a look at it. Okay? That's probably the easiest thing for us to do. Yes?
Can you do 8A?
Just trying to make this as out of order as possible. 8a. The point estimate is the same thing as the sample statistic, 3.47. The point estimate for a population mean is the sample mean. So it's really just testing some old terminology that we haven't talked about as much lately. Any other questions before we move on? To A? Yes. Yeah, a lot of people did that. They plugged these numbers into a formula, and it happened that something was really close to 0, and so you got 3.47. You can still show me if you want. I think I probably gave you some credit for it.
Oh, no, yeah, I got some. I made it.
It's just sort of by coincidence that you got the correct answer there. Yeah, yeah.
And subtract from 1.
Anything else? Okay. Probability. So we will start that, and we will get through this week. Then it'll be finals. So let me just say a few things about probability before we define what's relevant to us in this chapter. Every time we've made, let's say, a 95% confidence interval, we've dealt with probability, even though we have maybe not defined it. Essentially, saying, let's just say we said, there was a 95% probability that the population parameter was in the confidence interval. That's different than the way we have worded it in the past. In the past, we've said we were 95% confident that the population parameter is in the confidence interval. But another way of expressing that is to say, okay, there's a 95% probability, which, how do we interpret that? If you ran as an experiment this same sort of test 100 times, then 95 out of 100 times, the parameter would appear in the confidence interval. That's one way of thinking about these things. Or, if I say the right tail of z equals 1.96 is 0.025, which is 2.5%, on a standard normal distribution, I could think of this as the probability of something. What's the probability? So in this case, when we say this, the image we have in mind is this, hopefully, and an area shaded to the right of 1.96 is 0.025. And in what way is that a probability? Well, I'm saying if I randomly choose a z value on the normal distribution, the probability that the z value that I choose being greater than or equal to 1.96 is 2.5%. A randomly chosen z in normal distribution is greater than 1.96 about 2.5% of the time. Oh wait, sorry, I already said probability, so I need to say probability that z is greater than 1.96 is 2.5%. Okay. So there are two examples that are very similar to what we've been doing in the past, where you could reinterpret what we've done as probability. But we actually want to go and do sort of basic probability. Like things like rolling dice and flipping coins and drawing cards from a deck, that sort of thing. So how do we define these terms? Here's one way. The probability of an event A, which will always in this chapter be denoted P of A, is the proportion of times an event occurs. Some other just like basic facts about probability. The probability of an event A is always a number between 0 and 1 because it's a proportion. It can be 0, it can be 1. What else? If all events are equally likely to occur, which is often the case, but not always, then when you compute the probability of A, you're just going to look at a certain fraction. It's the number of outcomes in A that are possible over the number of possible outcomes. And those three facts are enough to get us started and talk quite a bit about probability. And especially this last one is pretty important. And so we'll just do some basic probability computations with that formula in cases where we're looking at a number of possible outcomes where each outcome is equally likely. So with that, it might be nice to talk about dice, for example. We'll do a really easy example. Find the probability of rolling a 5 or 6 on a 6-sided die. So if you have a fair die, when you roll it, each outcome is equally likely and there are 6 possible outcomes. Okay? So how many outcomes are in the event that I've just defined? 5 or a 6, right? So the probability that you roll a 5 or a 6, which we can kind of informally define like that, is the 2 possible outcomes divided by the total outcomes, which is 6. So 1 out of 3, 1/3 probability. Okay. Pretty simple idea there. All right, let's do something a little bit more interesting. Let's draw a random card from a deck of 52 cards. By the way, does everyone know what's in a deck of 52 cards? If I start asking questions about probability, it'd probably be good to know that. So you have 4 suits, right? And you have the numbers going from 2 up to 10, Jack, Queen, King, Ace for each suit. We're all comfortable with this, right? I don't know. Some people might have not played cards or not been allowed to play cards or something growing up. That actually happens. All right, draw a random card from a standard 52 card deck. Find the following probabilities. What's the probability of drawing a jack? How many jacks are in the deck? 4. No jokers, by the way, just 52 cards. So it's going to be 4 out of 52. Which is 1 out of 13. About 0.077, by the way. 7.7% chance. By the way, another way to think about it, so that you can get the reduced fraction as your probability, instead of the fraction we started with, 4 out of 52 makes a lot of sense. But you could think about the problem in such a way that you got 1 out of 13 as your answer. Because you could say, draw a card, you got some suit, right? Who knows what the suit is, but you got some suit. How many jacks are there of that suit? 1, and there's 13 cards in the suit. So you could have thought of it that way too. Either way, you're going to get the same answer. So this happens a lot with probabilities. You can think of the answer in many different ways. Hopefully all always correct. Let's go with another one. What's the probability of drawing a